It's a pleasure to introduce Giulia Illuminati. Giulia works at the National Institute for Nuclear Physics, INFN, here in Bologna. So she's at the Ionerio Berti Hall. She's our speaker today. She will talk about the cubic kilometer detection of these ultra-high energy neutrino. This is the field that she's been working on ever since her master, which she got in Rome at the University of La Sapienza. Then she did her PhD in Spain at Valencia, Instituto de Física Corpuscular. And then she was postdoc in Paris at the Astroparticle and Cosmology Lab of the university. And then she came to Bologna, first as a RTDA, and then now as a research staff at INFN. So, floor to Giulia, and thanks again for being here.
Thank you. Thanks a lot. Well, first of all, let me thank the organizers for giving me this possibility, and Marcello for inviting me to tell you a bit more about this very exciting latest discovery by the ChemTriNet experiment that detected the highest energy neutrino ever detected so far. So in this seminar, I will basically briefly summarize what we have reported in this recent paper in Nature, and also some extra studies that we performed in parallel and are in the process of being published as well. So first of all, a bit of introduction about high energy neutrinos and ChemTriNet. So ChemTriNet belongs to the group of high energy neutrinos, and usually by high energy neutrinos we mean neutrino with an energy that go from GeV to hundreds of PeV. So in this busy picture here, you have basically all the neutrino detectors available on the market nowadays as a function of the energy. So they exploit very different detection techniques, and also they can either look for, let's say, artificial neutrinos or neutrinos coming from atmosphere or astrophysical sources, which is more the case of ChemTriNet. So ChemTriNet is here together with IceCube, Antares, that you might have heard about. In any case, I will say something more later. And the blue area is the energy that we can cover. So as I was saying, mostly from GeV to hundreds of PeV, even though we can actually exploit some techniques to go down to the MEV region with the main goal of detecting neutrinos from core collapse supernovae. So what kind of neutrinos do we detect? In this plot, you have the neutrino flux as a function of the energy for different origins. So from the lowest energy in the cosmological case to the highest energy for the cosmogenic neutrinos. And so ChemTriNet is mostly sensitive to this region, which means that we mostly detect atmospheric neutrinos, so neutrinos produced in the interaction of cosmic rays in the atmosphere, and also what we call here neutrino from AGN, which in general means neutrinos from powerful astrophysical sources, which, as you can see, give rise to a flux that can be visible on top of the atmospheric flux at the higher energies. And then we also start to see the left tail of the expectation for cosmogenic neutrinos, which have never been detected so far. But of course, this is a specific model. There are plenty of models on the market, as we will see later. And also, as I mentioned, we can also go down to the MEV region, especially to detect supernova bursts. So given the wide range of energy that we can cover, we can therefore also perform several kind of studies using neutrinos. So starting, for instance, with a study of the properties of neutrinos themselves, like, for instance, oscillation and mass hierarchy, that we especially do with low energy neutrinos coming from the atmosphere. Then we can also look for neutrinos from dark matter, and usually what we do is to look for neutrino as the annihilation product of WIMPs, so weakly interactive massive particles from very massive astrophysical objects. And then one of the main goals of ChemTriNet is also doing neutrino astronomy, so using neutrinos to study the universe, and because neutrinos, as you know, are kind of peculiar particles because they are neutral and weakly interactive. This means that neutrinos can basically travel straight from the source. They are not deflected by magnetic fields, and also they are hardly absorbed by dense environments. So they are kind of I wouldn't say perfect messengers because they're also very difficult to detect, but in any case, peculiar and useful messengers for astronomy. So how do we detect these neutrinos? We exploit the Cherenkov effect. We deploy matrix of photomultiplier tubes deep down in the sea or in the ice, in any case in a transparent medium. And the goal of these PMTs is to detect the so-called Cherenkov light that is induced when charged particles that are produced in the neutrino interaction with the matter around the detector travel in the medium with a speed higher than the speed of light in the medium. So the neutrino that can come either from the cosmos or from the atmosphere, for instance, can interact through charge current or neutral current interaction. But in both cases, we have a lepton produced, which can be a charged lepton or a neutral lepton, so a neutrino, and a neutronic shower. In all cases, charged particles are produced, and this will give rise to the Cherenkov light. The Cherenkov light is emitted at a very specific direction compared to the direction of the particle that is inducing the light. And this is very useful because we know exactly at which angle it is emitted, which basically only depends on the refraction index of the medium. And so when we see the light, knowing the position of the PMTs, the time at which they detected the light, and the charge recorded by the PMT, we can basically reconstruct the energy and the direction of the parent neutrino, which is our main goal. Then, depending on which interaction took place and which neutrino flavor interacted, we distinguish between two main, let's say, signatures in the detector. So if it was a charge current muon neutrino, then this will give rise to a muon, and a muon can travel for kilometers in the detector. And all the many PMTs along the way are triggered, which makes it easier to reconstruct the direction of the muon, which is at high energy, collinear with the direction of the neutrino. So for this sample here, we have a quite good angular resolution. Then all the other cases give rise to so-called showers, in which the light is emitted in a very, like in a small limited space and in a kind of spherical shape. So the reconstruction of the direction is a bit more tricky, but this kind of sample allows for a almost calorimetric measurement of the energy. So we have a better energy resolution for this. And the high energy neutrino that we detected was a track-like event. So this type here. Most of the events that we collect in our detectors are atmospheric, of atmospheric origin, mainly atmospheric muons and atmospheric neutrinos. So in this plot, you have the expected the flux of particles divided into neutrinos in red and black, and atmospheric muons in blue and green, as a function of the cosine of the zenith, so the local coordinates that tell us the direction with respect to the horizon. So this part here is the downgoing events, so events that were produced in the upper sky and then reach the detector from the top, while this part here are upgoing events, so events that were produced, so particles produced in the atmosphere below the horizon, and then have to traverse the whole Earth before reaching the detector. So because of this, in the northern, let's say in the positive part of the plot, we are overwhelmed by atmospheric muons, which basically for all analysis are a background. But this overwhelming background can be easily removed, basically by looking only at the upgoing sky, in which we only are left with neutrinos, either atmospheric or cosmic. So this basically means that detectors in different locations on the globe have different visibility of the sky if we select only upgoing events. So, for instance, CameFreenet, which is in the northern hemisphere in the Mediterranean Sea, by selecting only upgoing events, will have a very will be able to see the southern part of the sky. So this visibility map is in galactic coordinates. So this is the galactic center. So it is able to see the galactic center and most of the southern sky and part of the northern sky due to Earth rotation. On the other hand, IceCube, which is exactly at the South Pole, if it would select only upgoing events, it would basically be able to see only the northern skies, which doesn't include the galactic center. Of course, this is an approximation because big detector can apply BITO techniques to basically reduce the background of atmospheric muons, removing the events that trigger the outer part of the detector. And this basically allows big detectors like CameFreenet and IceCube to open up the visibility to the full sky, which means that we are not really limited to half of the sky. But what remains true is that the part of the sky with the lowest background is the opposite compared to the location. So southern sky for CameFreenet and upper sky for IceCube. This is a map of the current telescopes that are either, let's say, taking data at the moment. So CameFreenet is being built in the Mediterranean Sea into different locations, as we will see. This is Antares. It was the precursor of CameFreenet. It was actually dismantled after taking data for 15 years. It was a much smaller detector, but it's still here because we are basically the same collaboration, and we are still finishing analyzing the data of Antares. Plus, there is a plan to combine the data of Antares and CameFreenet together now. Then in Lake Baikal, the Baikal GVT telescope is being built, while IceCube is in the South Pole. It is at the moment the biggest detector available. It is 1 cubic kilometers of instrumented volume, and it has been taking data for over 10 years, and it has produced most of the astrophysical results in neutrino astronomy that we have so far. And this is how the map will look like at some point in the future. So there are 3 different projects being designed in China, one project in Canada, and then IceCube is getting ready to upgrade into IceCube Gen 2. And now a couple of few words about CameFreenet. CameFreenet, as I said, is being built in the Mediterranean Sea, in particular in 2 different sites, Orca in south of France and Arca south of Sicily. Sites will be based on the same structure, which is called building block. A building block looks like this. It's a collection of 115 strings. So each string is something like this. It's basically a vertical line with each 18 of these spheres called optical module. And each optical module hosts 31 PMTs, which is the device that actually see the ceramic light. So there will be, in the end, 1 building block in Orca and 2 building blocks in Arca. But the main difference between Orca and Arca is not only in the location and in the number of building blocks, but most importantly in the density of the detector elements. So the space between different elements, both domes and lines, will be much smaller in Orca than in Arca. And this is because in Orca, we want to be more dense to be able to be sensitive to the GeV energies, with the goal of study mostly atmospheric neutrinos, to do oscillation and mass hierarchy study. On the other hand, Arca will be devoted to mainly astrophysical neutrinos, and this is why it is going to be bigger in order to access high energies from GeV on. And in this video, you can see basically, I think better, the difference between Orca and Arca. So yeah, I remind you that the number of strings and domes and PMTs is exactly the same, but what changes is the density. So as you see, Orca is extremely smaller compared to Arca. And at the moment, Orca is running with 24 active lines. So we have a yearly sea operation to deploy more and more lines, but due to the modular design, we can already take data and analyze our data. So we have 24 lines in Orca and 33 at the moment in Arca. Okay, I think, yeah, we can move to the main topic of the seminar, which is this recent detection of an ultra energy event, which came as a surprise because we detect such an unusual event with a kind of small detector, Arca 21. So Arca was taking data with 21 lines. The event passed in the detector 13th of February of 2 years ago. So what you see here is the reconstruction of the event. The event here is basically a muon, which most likely comes from a neutrino that interacted and produced a muon. So the straight line is the reconstructed path of the muon. The blue cone is the Cherenkov light, and all this, as you can see, a great number of PMTs actually was triggered, and so the event passing by. This number of PMTs corresponds to 35% of all active PMTs in the detector. And also, as you can see already from this plot, from this video, the event is kind of horizontal, yeah, and it's kind of in the edge of the detector. So, as I said, this event is kind of an outlier because it has some features that are kind of different compared to what we usually see. This can also be seen from these two different plots. So the left plot shows the simulations, so all of different kind of events that we expect to detect in ARCA, or in general in K-freenet. So the plot is a 2D plot that on the y-axis has the number of triggered PMTs, which is a proxy of the energy of the event. Usually the higher the number of PMTs that have been triggered, the higher is the energy, of course, given the same direction and position of the event. While on the x-axis, we have the cosine of zenith, so the same angle as before, so the direction that tells us where it comes from compared to the horizon, which means that these are downgoing events and these are upgoing events. And so in red, you have the yearly rate of atmospheric muons. So I didn't say that ARCA 21 was active, has been active for 1 year, roughly, so we usually compare the observation to what we usually see in 1 year of data. So this is what we would expect to see in ARCA 21 in 1 year. In red, the yearly rate of atmospheric muons that, as you see, as expected, concentrate in this part of the plot because there can only be downgoing events. And then in blue, you have the yearly rate of cosmic neutrinos, which have been weighted with the best fit cosmic neutrino flux that recently was reported by IceCube. And so the white line represents the contour, after which you find only 5% of white or 1% of event. And the location of the K-freenet energy event is here. So you see it is even in the region where we expect few cosmic neutrinos, according to the IceCube flux. It's basically on top of the 1% line. And as can be seen already from this plot, it has an enormous amount of PMTs triggered compared to the distribution that we usually see. So this was simulations, while this is the data that we collected in 1 year with ARCA 21, of course, where some selection was applied, the same selection that basically would allow to see the event. And as you see, we have most of our events in this part of the plot. They are most likely atmospheric muons. There are also a couple of events here which are instead most likely neutrinos, either cosmic or atmospheric, and these two events are under study at the moment. And then this is the location of the ultra energy event. So the main feature of this event is clearly the energy. So we tried our best to estimate the energy of this event. As I said, what we see is actually the muon passing through the detector. So we have first to reconstruct the energy of the muon, and then from that, give an estimate of the energy of the neutrino that produce the muon. So to do so, we use the number of trigger PMTs that, as I said before, is a proxy of the energy of the muon. So we simulated muons coming from the same direction at different energies, so 10 PeV, 100 PeV, and 1000 PeVs. And then we looked at the distribution of trigger PMTs that these muons would generate. And I mean, the different lines, solid and dashed, basically correspond to different values of some systematic uncertainty that we need to take into account, like the absorption length in water. And so from this study, we concluded that the best estimate for the energy of the muon is 120 PeV with this error, again estimated from this distribution. And then again, using simulations, we can give an estimate of the neutrino energy, which is 220 PeV with accompanied by this error. So this is as I said before, the highest energy neutrino ever it's observed so far, not only by K-freenet, but also by bigger telescopes such as IceCube. As far as the direction is concerned, so of course this is also quite important information. We can do this by, first of all, reconstructing the muon direction, which especially at these high energies is collinear with neutrinos. And we do this by measuring, by using the measured times and the positions of the hits at the different PMTs, and then we apply a likelihood algorithm that tells us which is the best, like the direction that best fit what we saw in terms of times and positions of the hits. So the local direction of this event is, as you could also see from the video, near horizontal. So it came from 0.6 degree above the horizon, so slightly downgoing. Unfortunately, at the moment, it is accompanied by a quite high uncertainty on the position, which is mainly due to the, let's say, poor knowledge of the absolute orientation of the detector. But we have some C campaigns scheduled to improve the knowledge of each detector element, with which we hope to be able to give a better estimate also of this event direction, because we can recalibrate the previous data. And so at the moment, the uncertainty is 1.5 degrees at 68% confidence level, and up to 3 degrees at 90% confidence level. From the energy of the direction, we can give an estimate of the probability that it is background. So here you have a reconstruction of what a particle reaching the detector with this zenith and also azimuth, of course, would have needed to pass through before reaching it, assuming that it came from above the Earth, so let's say atmosphere. So he had to go through about 120 kilometers of rock, because the direction is consistent with the position of the Malta cliff, and then several kilometers also in water. That in total makes 300 kilometers of water equivalent material, which makes it basically impossible that it is an atmospheric muon, because the yearly rate of atmospheric muons at this energy, considering also this the path that they would have needed to travel, is of the order of 10 to the minus 10. Of course, we could have also made an error in estimating the real direction, but even in the worst case of error of like 5 sigma, so basically an event being completed ongoing, still the rate remains quite low, 10 to the minus 3. And the other background option could be that it's an atmospheric neutrino. But also in this case, as you remember the plot from before of the atmospheric neutrino flux, at this energy, this is completely, let's say, overwhelmed by the expected cosmic neutrino flux. So also in this case, the probability that it's an atmospheric muon is quite low. It increases a bit if we consider that it is a neutrino from the prompt flux, but this is a number that comes from the most optimistic scenario from the prompt flux, which hasn't been detected so far. So this basically means that actually the probability that the real origin is astrophysical, let's say, it's much higher. So what kind of astrophysical origin can this neutrino have? So in order to make some hypotheses, we can first of all visualize it in a global neutrino context, which summarizes all the detection, limits, and predictions for neutrino fluxes that are available. The plot shows the neutrino flux as a function of the neutrino energy. And so first of all, we set this point here in the plot, that is basically the expected flux that is necessary to generate one event of this energy in ARCA 21 using the same lifetime and selection procedure. Of course, it comes with a quite big error, given the fact that we observed only one event. And so we can compare this with everything else on the plot. So, for instance, you have here the limits on the high end of the ultra high energy neutrino flux set by IceCube and Auger. So you see that the point in principle is above the flux of the limits, but however, if one takes into account the effective area of K3net and IceCube and Auger together with the lifetime and do some calculations, and you can see some details in this paper. Basically, the tension between having observed one event here and the limit is below 3 sigma, so it's still compatible with an upper fluctuation. Then we can also compare it with the highest energy neutrinos detected so far, all of them by IceCube. They belong to different samples, trapped showers, for instance, in pink and purple. And so, first of all, we see that our event is more than 1 order of magnitude higher energy of what was observed until now. So usually when we detect a diffuse flux of neutrinos like this, we then try to give the best fit values of the normalization and the spectral index, so the parameters that describe this flux, so basically how fast it decreases in energy. And this result is provided by IceCube, is given by this shaded pink and purple area. So if we extend, we assume that this flux can be extended at the ultra energy region, and so we extend it up to the energy of the event. We can use the K-infinite effective area to calculate how many neutrinos this flux would have produced in ARCA 21. And in the most optimistic case, this produces only 0.12 events. Which is, again, still compatible, let's say not in tension over 3 sigma, but at the same time, it is, let's say, marginally compatible. So it also hints to something different. So either, for instance, a different astrophysical object that produced the event, or a completely different origin, which could be, for instance, the cosmogenic case. Okay, in this plot, there are also 2 big bands. So one yellowish and one grayish. So these 2 bands basically summarizes basically a compilation of all available models for, in this case, diffuse neutrino fluxes from several astrophysical sources. So as you see, they extend over a wide range of energy and also predict order of magnitude different neutrinos. Some of them are quite powerful. So, well, first of all, the idea here is that neutrinos are produced in the source when where we have accelerated charged particles that can then interact in the source environment, which could be dominated either by matter or radiation. In both cases, we expect charged pions to be produced, from which we will then produce neutrinos. And basically, all these candidates here, gamma-ray bursts, pulsars, active galactic nuclei, and Tyler disruption events, for these candidates, there were some very promising fluxes, diffuse neutrino fluxes, which could, in principle, explain the event. And also, we have a paper in preparation in which we try to constrain gamma-ray burst energy and source parameters using the observation of the ultra energy event. And as for the cosmogenic hypothesis, again, the gray band is a compilation of all available models that for a diffuse flux of cosmogenic neutrinos. The 3 parameters are many, and this give rise to a big uncertainty on which could be the real diffuse cosmogenic neutrino flux. But again, there are some of the most optimistic models which indeed predict quite high flux. If we take the most optimistic one, we would expect 0.1 events in ARCA. So indeed, this could be also an option. And together with the Nature paper, we also published this parallel paper in which we investigate the cosmogenic origin of the neutrino. Okay, then another thing that, of course, we can do to see if we find some hint for the origin of this event is to look in the direction in the sky. Something that we did in this paper was to inspect the possibility that it came from a galactic environment. The galactic coordinates of this event are this, so it's quite offset from the galactic plane of 11 degrees, so which is already kind of hint that it is unlikely that it is galactic, but still we try to investigate some options. Here you have as I said before, the error regions, and for this analysis we decided to use the most conservative angle, so 3 degrees. So we looked for compatible sources in an error region of 3 degrees around the event. So something that we did was to look for potential gas targets that could act as a target for accelerated particles, for instance, for a diffuse flux of galactic cosmic rays. And in this plot, you have the map of carbon monoxide emission map that we investigated to spot molecular clouds. And as you can see here, there are 2 possible targets in the 3 degree region, which in principle could act as a target for accelerated particles and be the source of resulting neutrinos. Of course, this is a possibility. However, it is also quite unlikely if we take into account the expected fluxes of diffuse neutrino fluxes from galactic origin. This plot here is the flux as a function of the energy, and the purple band is a compilation of many available predictions for galactic emission. including, for instance, among others, Cra Gamma. It also shows the best fit results from IceCube, assuming the Pi0 model and Cra Gamma model. You might know that IceCube a couple of years ago reported the first detection of neutrinos from the galactic plane. And then again, this is the position of our event. So and the same bands as before for the cosmogenic and extragalactic diffuse flux. And while this is the atmospheric background. So the bottom line here is that the expected galactic flux are extremely low, and it's therefore unlikely that they would be powerful enough to then interact with these targets and produce neutrinos. And still on the galactic hypothesis, we also checked for the presence of galactic sources. We checked for supernova remnants, stellar clusters, X-ray binary, microquasars, and pulsars, as well as investigating these catalogs from Fermilab, Lasso, and Hawk. And we found 2 stellar clusters in the region, and as well as 2 unidentified Fermilab sources. Of course, once we have excluded the extragalactic non-Fermilab sources. And again, there are, which means that there are a couple of objects in the nearby, but usually models struggle a bit to predict very high energy cosmic rays and therefore neutrinos from galactic cosmic ray accelerators. So we can conclude that if the origin is, let's say, cosmic, so coming from an astrophysical source, it is most likely extragalactic. And among the extragalactic possible origin, we investigated the blazar option, being one of the most powerful objects in the extragalactic sky. So we investigated the equatorial coordinates of the event and also the arrival time in modifying Julian dates to also check for the presence of transient event or let's say flaring emission. So in the Nature paper, we reported 12 blazars identified in the error region, which is this one. So again, this is the map of the event in equatorial coordinates. This is the best location together with the different radii, and the biggest one being the one of 3 degrees. So after these preliminary, say, investigations, we actually collected more data. In particular, we performed dedicated VLBI observations with VLBA. And the number of coincident blazars in this 3-degree region increased from 12 to 17. So you have these 17 blazars were selected using 4 different methods. So and you have here the different sources numbered from 1 to 17 according to their distance from the event, while the different shapes here refer to the selection method. So the first method consisted in cross-checking several catalogs, X-ray, radio, and infrared. You have here details on which catalogs were actually checked. The second method consisted in looking in the radio fundamental catalog. Then we also investigated the FIS BZ catalog and as well as the Fermilab catalog. And of course, there were some overlap between sources. So we came up in the end with 17 blazars. And we studied these blazars using archival data that were available, together with some dedicated observations that we requested for the scope of this paper. Indeed, I mean, as you see, the number of blazars is quite high. We cannot make a certain conclusion on whether one of these and which one is actually the source of the event, because for the moment, the error region is too big, and we hope that it is going to be reduced with a future calibration, as I said. So what we could do for the moment is just study the multi-wavelength characteristic of these lasers to see if some of them would show some peculiar feature that might hint to a possible origin of the chemtrailnet event. And so something that we looked at was the time variability in the different wavelengths. And doing this, we spotted 3 interesting blazars. So one of these is blazar number 6, the source 0605-085. This is interesting because it shows a gamma ray flaring activity in the Fermi-Lat data. So you have here over a very large span, the Fermi-Lat data. So the event time is reported here in blue. So basically it came during a flaring activity, in particular when the gamma ray data, the emission was decreasing. And it's also interesting because this blazar is among the 50 brightest radio objects in the whole sky, according to the LBI flux density, which might hint to a high degree of relativistic binning. So this is one of the three blazars that showed most interesting features. Another one is this the blazar number 8, because it shows a major radio flare. So this is the flux density as a function of time over, I think this is 17 years of data. And as you can see, it is quite interesting because the event basically arrived almost at the same time of the highest peak, all-time peak seen in radio. In particular, the time difference between the arrival time of the event and the highest peak is only 5 days. So we try to estimate what is the chance probability for this to happen. Of course, as for sure you know, it's a kind of a tricky thing to do. I can give you more details on this. So we estimated that the pre-trial chance probability is only 0.26%, which means that it's not impossible for this to happen by chance, but not even that common. But of course, this number has to be taken with extreme caution because it's, first of all, an a posteriori analysis, and also we have to make some assumptions to estimate this. And this value could have changed making other assumptions. So it was just to give an idea of how likely it is just to see it by chance. And then the third blazar that we think it is kind of interesting is actually also interesting because it's number 1, so the closest to the source, and it shows some X-ray flaring activity. Again, this is a flaring activity in X-ray, function of time, and so we saw that there was some rising in the X-ray emission in Erosita. Happening a few years, the data stopped a few years before the arrival of the event. So we requested some observation in Swift, and we set this extra point, which seems to say that the emission basically raised in the years previous to detection of the event, and then let's say the emission persisted afterwards. But again, here we need to take into account that we have 3 years of gap of missing data. So it is still interesting, but we cannot say what was happening here. Okay, I think this was all for the blazars. Then also, in order to investigate the region, we also checked neutrino data in order to see whether this the neutrino data is consistent with the hypothesis of a neutrino source, a powerful neutrino source that we could have seen in using other data, for instance, the data of Antares, IceCube, and CaneFreenet itself. So we analyzed the 10-year public sample of Antares, as well as the 10-year public sample of IceCube, and also our ARCA and ORCA available data. And what we do here is only to rely on the neutrino data. So what we look is for a clusterization of events around the source location, because what we expect, of course, is that neutrino would clusterize in the vicinity of the source, so with a spread that depends on the angular resolution, and then while the background is more uniformly distributed. And then we also exploit the fact that the spectral behavior for the signal is expected to fall in energy much slowly than for the background. So we expect a harder spectrum here. So as I said, we analyzed this data, and this is basically the summary of the results. We expected a 3 degree times 3 degree regions around the events with a very fine binning of 0.1 degree. So the first column is the number of fitted signal events from each detector. Then we have the p-value, the upper limit on the flux in neutrino that we set from this region, the location of each spot that we identified, the distance and the final p-value, the post-trial p-value, taking into account the several trial. And so basically the most interesting results is we found using IceCube data with 15 events fitted at a distance of 2.4 degrees from the event. But the post-trial p-value is 7%, so it's not particularly significant. In any case, we are working on a refined analysis using private data and refined analysis method that we hope to be able to publish soon. Okay, I think this brings me to the summary. So ChemTreeNet has observed the highest energy neutrino ever observed so far, with an estimated energy of over 200 PeV. Given the energy and the direction of this neutrino, we can exclude that its origin is atmospheric, so it is most likely cosmic, if we don't consider also beyond standard model hypothesis. So possible explanations on its origin include a very powerful, most likely extragalactic astrophysical object, as well as the cosmogenic scenario. Sources in the nearby, so we have identified 3 close by blazars, which are interesting because they show time variability and also some flaring emission at the time of the event. However, for the moment, association with single blazar is difficult due to the angular error of the event, but it might become possible if we manage to improve the knowledge of the localization. We also checked for the presence of a strong neutrino source in the neutrino data of different telescopes, but we did not find anything significant. So we cannot derive any firm conclusion on the possible origin of this event. We need more of these kinds to be able to formulate other hypotheses. But as a fact, we have proved that neutrinos of such energy exist and that we are able to detect them. Thank you.
Thank you, Giulia, for a wonderful